So it's my pleasure to welcome Pallavi Jain, who's here despite the war breaking out close to her and Mumbai weather declaring war on all of us. So thank you for coming. Pallavi is a faculty at IIT Jodhpur. She works in ComSoc in graph algorithms, parameterized complexity, and mostly a combination of these three together. She before IIT Jodhpur, she was a postdoc at Ben Gurion and at INSC, and before that, she was a PhD student in Agra at the Alban Education Institute. So thanks, Pallavi. Please tell us.
Thank you all. Thanks, Raghuvansh. I don't know if Raghuvansh is not here. Thanks, Raghuvansh. So, yeah. So, I'll speak about FPT approximation algorithms for multi-linear rules, max coverage, and beyond. So, I'm not sure how many keywords are familiar to all of you, but we will go.
I know 100 of them.
Huh? Okay. So, okay, so I think Saket also gave a talk on FPT approximation. I recently came to know last year. But okay, there will be some overlap, but let's see. So maximum coverage, more or less, I think everybody know. But let's start with a fun example. So suppose you're planning your birthday party and you want to order cakes and nobody these days, I think nobody likes a simple vanilla cake these days. Everybody would like to have some toppings. So suppose you know that okay, these are the kind of toppings your friends would like to have. Okay, you go to a cake shop, there are some cakes available. Now you want to choose some cakes so that your most of the friends are satisfied, if not all. Of course, you want to satisfy everyone, but if you cannot, let's say you want to satisfy as many as possible. Right? So last cake image is generated by ChatGPT because I wanted so many toppings and Google image was not available. So if I look at these two cakes, then more or less every topping is covered. Okay. So this is precisely the coverage problem. Right? So if we look at the problem mathematically, we have a universe U, which was toppings in our example, and a family of subsets of U, right? Which was the toppings, set of toppings covered by a cake in the previous example, and an integer k. And your question is to find a subset of family of size at most k that cover maximum number of elements in your universe. Okay. So this is well studied in theoretical computer science. Now let's view it from computational social choice lenses. So
this is the same if I say that you want to find the K sets whose union is the largest.
K sets
whose union is the largest.
Exactly. So by coverage, that's a good point. So by coverage, we mean that look at the union of the set that you pick. The number of the elements in the union is your coverage set. Okay. So now what is the resemblance of this with multi-winner election? So this is one of the research problem, I would say, field, whatever you want to call it, multi-winner election, or it is also called as a committee selection problem. Let us see what is the resemblance. So election, as we think of election, is the same terminology. You have certain voters, you have some candidates. Okay. And every voter submit a list of candidates they would like basically to win. Okay. So we were like, there are let's say 3 candidates. I don't know, I don't care how many candidates, but this is the set. Okay. We can call it as a approval set. So V1 approve this green lady and blue guy. V2 approve this red guy and blue guy and so on. And now the goal here is to choose a K-sized committee that satisfies voter. So there are a lot of voting rules which differs based on the satisfaction basically for different terms. So one of the famous rule is Chamberlin Courant, which we also call CC in short. Chamberlin Courant are name of the people who gave this rule. So they say that a voter is satisfied if the committee has at least one candidate of its choice. For example, okay, the goal is to maximize the number of satisfied voters. So if you look at, let us say this is the committee, this green and blue, right? Then we can see that it satisfies all the voters. Okay. So, but if the committee size, let us say, was 1, then there is no committee of size 1 that satisfies all the voters. Okay.
So I should be thinking of these as just sets, right? And they're not like there is some preference between them or.
Okay. So this is called approval model of the election. But as you said, there are many other profiles. So we can see that there is a clear relation between Chamberlin Courant rule and coverage. Right? Do you see? Right. So what we can think, that universe is, let's say, my voters, because that is what we are covering here. And corresponding to every candidate, we have a set, right? And set contains the voters that who approve this particular candidate. Okay. So for example, this set, this green lady is approved by V1 and V3. That is why this is a set. Okay. So Chamberlin Courant is actually the maximum coverage problem. Okay. Okay. So there are more class of voting rules which are basically the generalization of your max coverage. Just for the notation, let us say C is the set of candidates, V is the set of voters, and AV is the approval set of a voter V. So Chamberlin Courant rule, if I want to define, we can say that if I look at a subset of C candidate, right, then my satisfaction of a voter is 1 if intersection is non-empty and 0 otherwise. Okay, so we can define it as a function. And now overall satisfaction, we are talking about the summation version. Utilitarian also we can call. So this is the total satisfaction of the voters. Okay. We can define more satisfaction rules. For example, one could be satisfaction is the number of approved candidates in the committee. Okay. You may see that this is same as the multi-coverage problem. Right? Number of times you cover an element, you count this, like in the score, you count that value. Okay.
Has this also been studied?
Multi-coverage.
Huh?
Multi-coverage.
No, multi-coverage, I'm guessing is probably studied. This thing of defining the satisfaction function as AV intersection S minus AV complement intersection S. In a sense,
Yes.
you also want to decrease the number of people you hate.
Yes, that is, I'm not just able to recall the name of the voting rule, but yes, this is one of the voting rule. So this is another thing, harmonic, right? So for every voter, I is equal to 1 to whatever is the size of the intersection and 1 over I. Okay. So this, this is max coverage, this is multi coverage, which are well studied even from the just TCS community. So this I am not sure, at least I don't think this has been much studied, right? But voting theory community has looked at it, right? So what I'm trying to say here that these two words are not different. It's just studied from different community, okay? But these are actually the same thing. Okay. Okay, so this all is fall under field voting rules. So we can define a function which takes a number and goes to rational numbers, and for 0 you map to 0. Okay. So for example, now what is the satisfaction of S is given by FV of AV intersection S. So for example, in case of Chamberlin Courant rule, FV of AV intersection S is if this is non-zero, then it is 1. For 0, it is 1. 0. Okay. And similarly, we can define everything. So we know that at least this class of voting rules generalize your max coverage and multi coverage. Okay. Okay. So let us begin with the maximum coverage problem. Okay. So here I am talking about the decision version of the problem. So additionally, we have integer t and you want to cover at least t elements of u. Okay. This is for convenience and one more reason which you will understand. But approximation algorithms, whatever I say, will work for even for the optimization version without T. In fact, in the paper, we write in terms of the optimality. Okay. So the problem is NP hard even when frequency of n.
Go back briefly, I missed a sentence. Find a subset of that covers at least one. Okay, so you're not maximizing, you just want a threshold.
Yeah.
Okay. Yeah.
You want to cover at least three. Okay. So this problem is NP hard even when an element appears in at most two sets. This is basically the partial vertex cover problem. Right? So this is already known to be NP hard. So once the problem is NP hard, we would like to study it from the approximation algorithms, classical, and now today's parameterized algorithms as well. So let's begin with the approximation algorithms. Okay. So in approximation algorithms, because we have K and we have T. So now the question is, what would we like to approximate? Right? So we can ask two questions. Either we can ask to approximate K or we can ask to approximate T. Right? So we can ask that you give me a subset of size at most K that cover at least alpha T many elements of U. Maybe not T, slightly less. Okay? Or you pick slightly more sets and cover at least T elements of U. Okay? So these both the questions we can ask. Right? These are studied. So if we talk about, this is the main focus of the talk, that is why I'll focus on approximating T. Okay. So the simple greedy algorithm that you pick a set that cover maximum number of uncovered elements. This gives you 1 minus 1 by E approximation. Okay. This is a very old algorithm and we cannot improve it in polynomial time. Okay. Okay. So the previous result, so this result basically closes the door of approximation algorithms in some sense, right? We have 1 minus 1 by E and in polynomial time we cannot improve it. Okay. Okay. So now let's talk about the parameterized algorithms. So again the question is, what parameter would you like to consider? Okay. So I'm not sure how many of you are familiar with the parameterized word approximation. Maybe it's a very old field of algorithms, people know. So for the purpose of today's talk, don't worry about it. You don't need any background of the parameterized algorithm. The talk will be accessible to you. Okay. So just think that along with the input instance, you also have a parameter, some integer. Okay. So if the parameter is K, here K is our same K. Okay. Such that I want to pick. Then I would like to have an algorithm whose running time is of this nature. What does it mean? My algorithm, my running time can have exponential dependency on the parameter. But on the input size, I is the input. Okay. On the input size, we are only allowed to have polynomial dependence. Okay. Okay. If such an algorithm exists, then we say that the problem is FPT with respect to the parameter K. If not, then there is a class of hardness in the parameterized complexity word, which is called W. So if there is no hope for such an algorithm, we say the problem is W hard with respect to the parameter K. Okay. So just a bit of technicality, which we can ignore for today, that in general, it is not W hard. There is also an integer associated with it, WT hard. So we say problem is W1 hard, W2 hard, so on and so forth. But for today's purpose, we just can focus on the fact that with respect to this parameter, I cannot hope for FPT algorithm. That's it.
Do you have just like you have SAT that is complete for NP, do you have a complete problem for W?
Yes, W complete problems also we can talk about.
Is there a simple example?
That's not on top of my head. Click. Click is W complete.
I'm just saying something.
Yeah. No, it's not, because they are like completeness is not like we do in NP complete. So yeah,
Given result is hard for W1.
Yeah.
Yeah.
Click is also W1 hard, but this set cover type problems are W2 hard.
So when you say that something is W hard, it's not a conditional statement. You're saying there is no FPT algorithm.
I mean, condition is like there we have P not equal to NP, here FPT not equal to W. So yeah. So similarly for the parameter T, we can think. So this parameter in general could be anything. It could be any input parameter of the problem, output, or structure property, right? But I mean, we don't need to go too much into what is parameter and all those things. The only thing is that this is my parameter and this is the kind of algorithm I'm looking for. That's it. Okay. Okay. So with respect to parameter T, FPT algorithm is already known for the maximum coverage. Okay. Now the next question is K. So the problem is already known to be W hard. Now in terms of hardness, we know that the with respect to parameter K, the problem is hard. Polynomial time, I cannot achieve such kind of approximation, right? So the next question is, can we merge these two words? So can we achieve 1 minus 1 by e plus epsilon approximation in FPT time? Okay, FPT in K. Okay, here also the answer is no. Okay, even this we cannot hope for. Okay. So now what next? Okay. Next thing is to restrict the maybe one of the direction is to restrict our set families. Okay, to explore the structure of our set family. Okay. So next question we ask. Fine, I know that the problem is NP hard even in this restricted setting. Okay. So I have this and I have those. Do I still have those hardness? Right? So meaning partial vertex cover, is it W hard with respect to K? And this kind of polynomial, this kind of approximation thing. Okay. So this is also true. Right? Now it makes sense to ask this question, and such kind of algorithm. Okay. So frequency is bounded. We are looking for better than 1 minus 1 by E approximation in FPT K time. Okay. So here we have positive thing. Okay. So Scan has Scan gave this algorithm that when the frequency of every element is bounded, right, then there is 1 minus epsilon approximation that runs in FPT time. Okay. And this is the starting point of our research. Okay. So we will look at the set family, which is the larger class of this family. Okay. So we'll look at KDD free set families. Okay. So KDD free set family is basically no D sets in the family can cover D common sets elements. It's better to visualize it in terms of graph.
Go back. What was the dependence on D in star and scissor?
Yeah, the running time has I'm not writing the running time, but this G, this running time has K, epsilon, and D.
So it's also in the exponent there?
Yeah.
Okay. But K is not in the exponent. T is in the exponent.
K is also an exponent.
No, the exponent
I to the order running.
Oh, yeah. D, even D is not there.
Oh, so it's
That part is a strict polynomial.
I see.
This G of K part has K, D, epsilon.
Okay.
So D does not necessarily need to be a constant.
So when we say bounded, by definition, it means that we are talking about constant. That is why we ignore those terms.
Okay, but it doesn't appear in the exponent in the input size.
It doesn't appear. Yeah. Okay. Yeah, any other question? So in KDD free, at least I find this definition confusing. Let's see this in terms of graph. Okay. So we can look at the incidence graph. Okay. So one side is my family, other side is my universe. And this is simple incidence relation. Okay. So we have for every set in the family, we have an element. And for every element in universe, we have a vertex. Right. Now V1, V3, this vertex is adjacent to elements V1 and V3. Okay. Now KDD free set families, meaning this particular bipartite graph does not have KDD as an induced subgraph. KDD meaning complete bipartite graph where both the sides have D. Okay. We can also talk about AB. There's no issue with that. Everything works. It just for the simplicity, we are talking about KD. Okay, and we can also see that if a graph is KB free, whatever is the maximum, let's say B is maximum, then it is KBB free. Okay. Okay, so this particular graph, we can see that it is K22 free. Right. Okay. Now, if a graph has bounded D, D frequency, right, then clearly it is KD plus 1, D plus 1 free. In fact, it is KD plus 1, D free. Okay, but this is also fine. KD, D plus 1 is also. Okay. So, if this is a no three families share an element, and like this is the meaning of K22 and K313, but actually I've written it like this, but it is nothing but vertex cover, partial vertex cover. Okay, but just to relate it with the KDD freeness, I've written it like this. So let's
Is it exactly what it's saying?
Yeah, partial vertex cover. Yeah. So let's look at the pick K sets of maximum size. Okay. Clearly, if these sets are disjoint, this is the best I could hope for, right? Because if whatever this K sets can cover, right, nobody else can cover more than that, right? But now the problem is that
Not right, because here there may be pairs.
overlapping.
No, but in vertex cover, you know that every edge has two vertices. That's in two sets.
Yeah, right.
Here
right.
it's not guaranteed, right?
Okay, PDC has this property.
So what is a partial vertex cover mean? What's partial about it?
So in partial vertex cover, you don't want to cover all the edges. You want to find a subset of vertices that covers at least T edges.
Oh, I see. Okay.
Or at least T edges.
Yes, at least T edges.
Yeah, I see it has these properties. I don't see why it's the same thing.
So
This is one thing in graph, right? You have an answer state, you can consider a graph where the family here is the
So an edge can contain is like endpoint of two vertices.
Yeah.
You're right. If a graph has this property, it need not capture the graph. But if the graph has this, that has this property.
That I agree. One
Yeah.
way is right.
Yeah, you're right. Okay. So yeah, if these sets are disjoint, then of course this is the best you could do. Pick K sets of maximum size, right? But the problem is overlapping, right? Okay. So, but how much overlapping can we have? Right? Because look at two sets, right? It is K22 free. So they can share only one element. Right? So we can have sharing of at most K square using those K sets. Right? Again, we can think of that in case it is actually K choose 2. Okay. So we can think of that, oh, if there is an overlapping, I can put an edge. So how many edges can be there? K choose 2. Okay. So they can be overlapping of at most K choose 2. Right. So if opt cover at least T elements, I know that I will definitely cover this much T minus K choose 2. Okay. Okay. Now, if K choose 2 is less than equal to epsilon T, right? Then we just substitute it and we know that we covered 1 minus epsilon T. Okay. The problem is it is large. But if it is large, what do we know? T is less than equal to 1 by epsilon K choose 2, right? So T is basically bounded by function of K and epsilon, right? So run the FPT algorithm with respect to T that solves your problem optimally. Okay. So and this is exactly the part which is giving us FPT running time. Of course, this is the polynomial step. Okay. This is not our algorithm. This is already no algorithm. Okay. Any questions here? So just simple algorithm. Okay. Now, if we talk about KDD free, okay. So indeed, we don't have K choose 2 bound, but could we get some bound? Maybe in terms of D. right? So if I look at these sets, then indeed they can share at most d minus 1 elements, right? But if I look at d minus 1 sets, I don't have any control, right? So this intersection could be large, okay? So at least immediately things do not work, right? Immediately we don't have any bound. Okay, let's look at the problem again. We have this incidence graph, right? And let us say we look at the large set of highest degree. It's not just K, some large set, okay? Let's say this is my optimal. Now, why I'm not able to kick out one blue vertex and put one black vertex inside? Why? Because I know that this black vertex covers more than this blue
What do you
vertex
mean by
because of
set
the
of
degree.
highest degree?
Just sort it and pick the vertices of highest degree.
So those black nodes correspond to sets, and those are the highest.
Yeah.
Uh,
So like look at
it's
this.
just so like the highest cardinality on their own, or is it a really way of?
On them.
So this black, this is a simple thing. Now, but the problem is the overlapping. That's the only problem, right? Okay. But now the question is, indeed, in general, we could have a lot of intersection, but because my graph is KDD free, right? Then can I do something that, okay, intersection is bounded, maybe not in general, but with the high degree set, so and so forth. Okay. So let us look at a element in vertex in in F, right? Let's look at its neighborhood. Okay. Now, these are the sets which have high intersection with the neighborhood of S. Okay. By high, let's say beta high, and by high I mean neighborhood of S by beta. I will set the beta some later. This is just some value. Okay.
So, S is a high cardinality set.
S is some set at this point of time. Yeah. So S is some set, and these are the vertices which have high intersection with its neighborhood. Okay. In general, this can also be large. Okay. But if I look at the within this set, if I look at the vertices whose degree is large, by large you mean D, at least D. Okay. So AHD is a set which has these vertices which have high intersection as well as neighborhood is that is size. Size of neighborhood is at least D. Okay. This we prove that we can bound by a function of beta and D. Okay. Using some KDD free problem. Now what happens? When we looked at that black vertex and blue vertex, right? I was not able to.
How complicated is that problem?
It's not it's just some maths, not very complicated. Just need to use, okay, how many neighbors can be shared here and there. And that in the paper we proved it, but that also comes from some known inequalities. So in the previous picture, when we tried to kick out that blue vertex and put black vertex inside, right? We were not able to do it because it had large intersection with the already existing sets in my solution, right? So now the idea is that, okay, either one of those sets in my solution, or if they are not in the solution, then I can take my this highest degree vertex. Okay. Okay. So idea is this, we will look at the algorithm, but suppose that a max degree vertex is sufficiently high. Sufficiently high also we need just for the technical purpose. And if it is not high, then again we can run our FPT in T algorithm. Okay, and solve the problem optimally. Okay. So AHD neighborhood of set AHD of neighborhood of X, right? Now we will do just branching. We will say that either X is in my solution or one of this vertex is in my solution. Okay. And we say that addition of like one of the branch incur less loss. Okay. Oh. So this is the algorithm. K less than or equal to 0, we can't cover anything, fine. So if delta F meaning a maximum degree of an element in F, right? If that is bounded by 2 beta D, then we know that together also you can only cover 2 beta D into K many sets. Right? So if T is larger than that, we know that it's no instance, right? Otherwise, you just run your FPT in T and solve the problem optimally. Okay, so that is what I meant by degree sufficiently high. Okay, okay. Now look at a vertex in here, right, with the maximum degree. Okay. We compute this AHD and beta just for the technical reason. Now we look at for each y in X and neighborhood. Basically, this is just the branching step. Okay, so you delete it. When you delete this vertex, you also delete its neighborhood from the graph, right? And you just recurse.
Okay.
Okay. And whatever give you maximum, you return, and at the end you just check if something is giving you 1 minus epsilon by c, epsilon into t. Okay. Okay. So let's see why is it correct.
Sorry. Sorry. There was a bound on the AHP set.
Yeah. Oh, okay. That proof, if you want, we can discuss later. I
It's
will not
just a
tell you.
bound. So
Yeah.
this here has some bound which has a small t in the exponent.
Which has a small.
Yeah.
Small t in the exponent.
Yeah.
And then the next thing, there was a loop which went over all elements in A.
So yes, the running time will have this to the power k.
I see. So the small t and this is the same small
This
t.
d is the same as kdt.
Right.
Okay, so we just prove by induction on K. So we can ignore the base case and induction hypothesis. Okay. So let us say Z is your X union or this thing, right? Now there are two cases. Either your opt has something from Z or it does not have. So let us analyze both the cases. Let us say opt intersects with your Z, right? Let's say this is an element Z. Delete it and look at your opt prime. Okay. Now, what do we know about opt prime? In the remaining graph, GZ, remember how did we define? GZ is delete Z and its neighborhood. Okay. So, it has to cover at least this much, right? Otherwise, it contradicts that opt covers D. Right? Okay. Now, due to induction hypothesis, what do we know that when you call for GZ, K minus 1 and this, all these things, I know that you are getting at least this much. Right? 1 minus epsilon of this much. Okay. Okay. Now if I add back Z, I have this inequality, like simple inequality. And you solve it, you get it 1 minus epsilon t because you can like solve this thing. Okay. So if opt has something from Z, right? We know that we can achieve 1 minus epsilon fraction of t. Right? 1 minus epsilon into t.
Where do you use the fact that small z is a part of capital Z?
This thing. In the induction hypothesis, right? So because it was part of Z, we know that if I look at G is ZZ, then it covers it at least this much. So SZ cover at least this much.
But wouldn't that always be true? Because if it doesn't cover that much, even if you add Z, it cannot cover T, right?
No, we add because if you add back Z, it will only bring neighborhood of Z.
Yeah.
Right? So if neighborhood of GZ is less than T minus neighborhood of Z,
Yeah.
the coverage is less than T.
Yeah, agreed. That's what I'm saying.
Yeah.
You didn't use the fact that it is capital Z.
Oh, okay. That is used here, right? I removed Z from opt,
Yeah.
right? So because of that, I know that opt prime this thing, right? And I run the algorithm only for the element, like branching algorithm. I run only for the elements in Z. That is why I know that I have SZ. Yeah.
Okay.
Okay. Now let's look at the case when it does not intersect. In this case, now in some sense it is like that is our intuition. That if opt does not contain anything from the Z, right, then even the highest degree vertex X is good enough for me. Because whatever is in the opt, you don't have large intersection. I'm going faster. Yeah, so X union Sx is a desired solution. We want to say that. So look at F. F is the set. I'm just using the terminology interchangeably. So F is just a set in your opt that cover least number of elements alone. Okay. So neighborhood of opt is some value t prime, which is greater than or equal to t. So we know that this covers at most t prime by k, f. So neighborhood of opt prime is at least this much, right? Okay. We assume we are in the case when the max degree is large, right? So neighborhood of like again some just calculation. So max degree is x is the vertex of largest degree. So neighborhood of x is delta f. So neighborhood of x divided by 2 beta is greater than d, right? Now, if w is not an element in your AHD, right? What does it mean? Two cases, either its degree is small or its intersection is small, right? Because two conditions were applicable. So in both the cases, we know that it is less than or equal to neighborhood of x by beta. So opt prime covers at least this much in Gx. Overall, it covers t prime minus t by k, but it may have some intersection with the neighborhood of x, right? But that intersection is bounded. So in Gx, it covers at least this much. Okay. Now, again, if we use the induction hypothesis on Gx, then we know that we get a set Sx, right, which covers at least 1 minus epsilon of that value. Right? Again, now neighborhood of x union Sx, do the computation, put beta equal to k by epsilon, and we get 1 minus epsilon of t prime. Okay, any question here? We can take a pause. Okay. So, its running time is because of the branching factor, we have this part. Okay. And in case of if we use FPT node algorithm, right, then we get this is the running time, that is 2 to the power of order t. So this and we can see that this is the leading factor, right? So if we use the known FPT algorithm, then this is the running time. But we also designed a kernel, which is just a pre-processing method, right? And using that, once we have that kernel, meaning we pre-process the graph, obtain a smaller instance of the same problem, equivalent instance, right? And then if you do brute force, then this is the running time. So eventually the running time is dk by epsilon order dk. Okay. Okay. So maximum coverage story is over. Now we will generalize it to the broader class of voting rules. Okay. So I have not covered it here. I focused on the just set cover part, right? But we do have similar result for the max set as well. Satisfiability problem. Okay. Okay. So now let's just quickly recall field voting rules. So
What
this
is the parameter for max set?
same parameter, same class of family KDD.
So every D clauses, they don't have D variables in them.
Yeah. So, do you all remember this resemblance with the max coverage? Okay. So, let us just quickly see, because we will talk in terms of the incidence graph again. So, terminology is same. Okay. We have family, we have universe, and yeah, candidates. So, we know that the set corresponds to a candidate here. Right? Everything is same. Okay. Okay. Now, we looked at this function, right? So I will be talking about the function which are non-decreasing. Okay. So just to emphasize this thing, that corresponding to this, we can define a function which takes a subset of the candidates and map to an integer. And if this is the function, then it is monotone and submodular, considering that it is non-decreasing. Okay. Why I said that we don't need to go into why is it monotone submodular, you can believe me on that. But the point is that is why for this class of functions, we again have 1 minus 1 by e approximation using the known procedure, known greedy algorithm, right? And which is also tight, that we know, right? Okay. So, for the technical purpose and also for this is how it is studied in the literature of multi-winner election. For every I greater than equal to 1, this margin we define as the lambda I. Okay. So now satisfaction is the summation of these lambda I values. Okay.
Sorry, what is set? I thought you defined set in terms of a set.
Set I defined in terms of
A set. What is set of I?
set of I. Oh, you're right. I should say here FV of I.
FV of I.
Yeah, F of I, basically. I mean, if we want to ignore B, it is F of I. Okay. Because, yeah, you're right. Set I defined in. Okay, I just mixed up the notation. So, set, imagine that as a number for now. This F is same as set. Okay. Okay. So, this Chamberlin Courant is again the same thing. F set. I think we remember this details, right? Okay. So this thing is to note that lambda b for the Chamberlin Courant is 1 followed by all zeros, right? Because what did we say? After 1, like coverage remain the same. Okay. Okay. So this when you have n many ones together followed by all zeros, right? Then this approximation is given by Berman et al. Right? So we can see that for an L is a 1, like 1 followed by all zeros, it is 1 minus 1 by e, same as this, right? Okay. So again, in the parameterized algorithms point of view, we ask the same question, parameter k, parameter t. Of course, it is the generalization, so hardness do follow, right? So, but in case of parameter t, it is open, but we give FPT for certain cases. This is recently accepted. And for PAV rule, this is called proportional approval voting rule. But we can ignore the name and focus on the class of functions. So it was poses an open question whether it is FPT with respect to T. Which is,
So now T is the target value for set of S.
okay. So we will just quickly look at it just to understand the frame, the algorithmic technique, and it's a very simple randomization algorithm. Okay. So what we want to do, we highlight the voters that are covered, and you also highlight the candidates that are in the solution. Okay. So you just do coloring. Okay. So these are the color candidate set partitioned according to the color class. Voter set partitioned according to the color class. Now, what is the meaning that basically my solution candidates are colorful and the voter set that is covered is also colorful. Okay. So now, because it's not max coverage, in this particular setting, a particular candidate can give score to multiple voters, right? Because of all lambda. But what we want is, we want to pick one candidate from each color class, right? But what I don't know at this point of time, okay, this candidate in the optimal solution, right? Whom do you want to give the score, right? So let's just guess even that. So you guess that, okay, if I pick something from the first color class, right? What all voters will be covered? You guess all these edges, K, T, it's fine, it's still function of K and T, right? You guess it, and then you just need to find a candidate here which has, which is approved by the voters in your neighborhood. That's it. So it's a simple, running time is of course not great, but this is one possible algorithm. But currently what I said has K and T both in the parameter. Right? Because you are highlighting voters as well as you are highlighting candidates, right? So if K is a function of T, bounded by the function of T, then it is a FPT in T, right? And for PAB, okay, I think we can skip this, the exact running time. Okay, so for PAB, we can actually bound it. That is why we get the FPT parameterized by T. Okay. Okay, so one question is that can we improve this algorithm? And can we get FPT in T for general monotone and some modular functions in general? Okay, so I have just 3 more minutes.
Yeah. 13.
Yeah, 3 minutes.
Oh, I have 13 minutes.
Yeah.
Okay, then it is more than enough, I think. So now we are done with the parameter T. So let's focus on the parameter K now. Okay. We know because for max coverage, same hardness are we have here. Basically, we want to ask that if for KDD free, here also we have same hope. Okay. So we partition it into 2 cases. Okay. Based on our threshold value. Okay. So in our case 1, basically I will reduce the size of the candidates. Candidate set size I will reduce, apply the brute force, do something. And here we will do some algorithm. Okay, but I will just quickly discuss these 2 things. R and R are just these 2 values. Number just for mass workup. So here, I'll just introduce a toolbox in parameterized complexity world, which is sunflower. So it is defined for arbitrary graph. Okay. So this for bipartite graph, it is defined and recently given some lemma. This is just to give the better bounds. Everything works even if you work with the classical sunflower lemma. Okay. So what does it say that? So you have a bipartite graph. Okay. Now a subset of this candidate set is called a sunflower if the intersection of all these sets is same. Okay, so for example, if I look at 2 candidates, right? Every 2 candidates always form a sunflower, right? But here in this particular example, we can see that these 3 do not form a sunflower because for this green and blue, intersection has V1, right? But for blue and red, intersection has V2, right? So for every pair, intersection is not same. Okay, so that is why it is this 3 do not form sunflower. Size of sunflower is the size of this set. Now recently, Manramsi proved for KDD free that we can ignore what are these precise values, but if the size of the candidate set is large enough, then you have a sunflower size, some size W, right? Which can be found in polynomial time. Okay. Why these numbers are interesting, we'll just get to that in a minute. Just one point that he proved the result for, again, general KAB, then candidate set everything has A and B there. Okay. I'm using in terms of D because we need in terms of just KDD. Okay. And it is easy to understand instead of following too many variables. Okay. So what we do, suppose that there exists a voter whose degree is large enough. Okay. So remember, this is our T, right? And if it is lambda min, right? Lambda min is first lambda minimum of lambda ones for all the voters. Okay.
What is minimum? You mean eigenvalues or?
Not eigenvalues. So we had vector for all the voters, lambda 1, right? So first coordinate, min of first coordinate, lambda 1 values for all the voters. Okay. So because we know that if degree is that much, right? So for every voter, it will contribute some value, right? So this is the desired solution, right? Now we know that degree is not very large, degree is small. Now you can see that every vertex in C has degree at most L, and this is my L, right? And I pick W as LK plus 1. You'll just understand in a minute why this thing. Now, if my candidate set is larger than the split the values, right? Then we have a sunflower of size LK plus 1 basically. Okay. Now what we do with this sunflower, we have a large sunflower. Look at the candidate whose contribution is small, right? Delete it. Right. So you see that we deleted we just delete the candidate, nothing else. Okay. So if the candidate set is large enough, we always have a guarantee to find a sunflower of this size, right? And then I can always delete this vertex. Why is it safe? That we need to argue, but at least we know that if it is safe to delete this candidate, then my candidate set is size is reduced. Okay, and reduced by we can see D, K, R was also function of this KRD lambda, right? Just by these values, so I can do brute force now then and solve the problem.
Curious about the lemma. So the standard sunflower lemma would have an exponential, like the dependence on the set size will be exponential in W.
That is why.
So what is W in this thing?
W is just some number.
W is the size.
Oh, W is the size of the sunflower you're looking for.
Correct.
So the typical dependence would be exponential. Even if the conjecture was true, it's going to be exponential in W.
Correct.
So the gain between this here
Correct.
and there is that D we are assuming to be tiny, W is potentially
Correct.
large, and so
Correct.
it's much better.
Yes. Right. Okay. So so suppose that this was safe to delete, then we agree that in FPT time we can solve it optimally, right? Given that bound of T, right? Case 1. Okay. Okay. So now let's quickly see why is it optimal. So backward direction is easy, right? If in the reduced instance you have a k-sized family that covers your T set, then we are done, right? Forward direction is something to RP. So let's just quickly look at the. Okay, if S does not contain U is the vertex that we deleted, then also we are good, right? Now suppose U contain U. Remember that the candidate has degree at most L, every candidate. Okay, so this can cover at most LK voters, right? So that is the idea. Because our sunflower is of size LK plus 1, I know that there exists a candidate whose neighborhood is completely untouched by our solution, right? So I can delete this U and add this V. I know that V covers more than U. Like V gives you the score value more than U because U is the one with the least score value that we deleted, right? So I'm not sure if the picture is clear. I tried. So for every candidate, this blue and red is its neighborhood. Okay, and red is the common part. So this is the disjoint part. So what we know, if I pick K sets and at most something I could hit, there will be definitely one petal which is completely untouched, right? And that is the particular candidate I pick in my solution and delete Q. Okay. Okay. And that's it, because I know that let us say this is my V, right? So, and let's say C4 is my U. So I know that this red part is anyway as much as covered by U, also covered by V, right? I delete one, add one. And in this part, if I can see that these vertices or these voters, right, maybe are covered by someone else as well, right? So they were giving some value, could be lambda 1, could be less, right? But for these voters, I know that this particular candidate is definitely giving lambda 1 because this is completely untouched by other candidates. Okay, so this is how this gives us better score. Okay, so now case 1 is, any questions in case 1? So in case 2, when it is large, again, so I'll quickly complete this part. So if I look at okay, this is some large set of high degree vertices, and we can say that there exists a subset in this set, right, which is good for us. Meaning I can pick it and this does not have too much of loss. Okay. And this set is also not very large. We can argue that this much size is good enough for us. Okay. So then I can try all possible subsets of size K, and whatever gives us best is the solution. Right. So we only need to argue the existential thing that there exists a solution with less loss in our high degree set. Right? Okay. So what we just do this iterative procedure that let us say L is some values. So there is some intersection. So L is the extra value that you are getting. Sorry, L is not the extra value. L is the set that are not in the intersection. Okay, so we just delete a vertex. We can delete any vertex from opt, right, which is not in the intersection, and put a vertex which gives us which minimizes this loss. Okay, so this black vertex which I entered in is the vertex which minimizes the loss, right? And that loss, let's say we call alpha I, right? We keep repeating it, and we can show that this summation alpha I is not too much. Okay. Okay. So this running time dependency is order d square k. So in the previous algorithm, when we had max coverage, the dependency was just dk, right? Indeed, when we say KDD free families, we assume that d is constant, but still there is some dependency, and we can try to improve that. That's like an open question. We can improve it. Okay, so now I will just quickly introduce the field of lossy kernelization. Okay, so like in case of FPT word, there is kernelization. I just briefly talked about that during the talk. So you have a parameterized problem, and let's say ik is an instance of the problem pi. This k has nothing to do with our coverage problem. This just k is an integer, which is our parameter here. Okay. Now in polynomial time, we want to have an equivalent instance I prime k prime of the same problem. This is important in the kernelization. Okay. Such that size of the instance is bounded by function of k. Right. So it is well known that if a problem admits FPT algorithm, then there exists in kernel. Right. But that kernel, so once we have an FPT algorithm, we know there is a kernel. But that kernel can be of exponential size. So the interesting part is that can we have a polynomial sized kernel? Okay. Okay. So for the max coverage, we have a polynomial kernel with respect to the parameter t, which we actually used in our algorithm, right? And in case of generalized Thiel voting rules, again we have in certain cases, if k is bounded by a function of t, then we will have, otherwise not. Okay. And clearly, because with respect to the parameter k, there is the problem is W hard, so we cannot have polynomial kernel. We cannot have kernel. Forget about polynomial. Okay. So, but we do have FPT approximation scheme. So similar to FPT and kernel, in the parameterized approximation field, there is a lossy kernel. Okay. So what does it mean? I'll just introduce what it is. Okay. Pi is so this of course we look for when we do not, when the problem is W hard, we design FPT approximation scheme. Then next thing is this step. Okay. So we can reduce the size of the instance at the cost of exactness. What do we mean by that? This part is same, that in the ik is an instance of the problem, and I am creating another instance of the same problem which is bounded by function of k, but if the property is this, if you give me alpha approximate solution of the reduced instance, then in polynomial time, I can lift it to alpha beta approximation. And this is called beta lossy kernel or beta approximate kernel. Okay, this was introduced by Lakshmanov et al. In 2017. Okay, so similar to FPT and kernelization, here also we have this relation that if a problem is alpha FPT approximable, then with respect to a parameter k, then there is the alpha approximate kernel with respect to the same parameter. So here also the interest is to design a polynomial size kernel. Okay. So we designed a 1 plus epsilon approximate kernel for KDD free families with respect to parameter KD epsilon. So this is in general. Again, this also use sunflower lemma and couple of more techniques. Okay. So the talk was based on these two papers, and most of the authors are same in both the papers. Okay. So this is our IIT Jodhpur campus, and you all are welcome to visit. Oh, thank you.
I was wondering about kernelization. Is it an if and only if that you have kernelization if and only if with FPT?
And when you say that you have a 1 minus epsilon approximate kernel, you mean a polytime obtainable kernel?
Yes. Yes. So in kernelization, running time is always polynomial. But one thing to note here is 1 minus epsilon approximate kernel, it means that in the approximation, again the loss is 1 minus epsilon. So if you give me alpha approximate solution of a problem, then with some 1 minus epsilon loss, again I'm giving you I'm missing.
And so you talked about approximating K and T separately. What if I wanted to do both simultaneously? If I allowed you some slack in both?
Yeah. So if the problem is W hard, let's say with respect to both the parameters, then it does make sense to talk about both the parameters together.
Sure. Okay.
So for example, FPT for max coverage, we already know FPT with respect to T.
Yeah. Yeah.
But like this three voting rules, so we don't know. So the this thing randomized algorithm that I said, which can be de-randomized using a perfect hash family, that has parameter K plus T.
I see. I see. Okay. When it comes to approximation algorithms,
So if K plus T already we have FPT algorithm, then we don't want to approximate. We can think. So we can think like this there, that let's say we know that in a K plus T running time we cannot improve, right? In the optimal sense. Then in better running time and we get some loss.
I mean in polynomial. I mean polynomial running time.
Polynomial running time, and then what?
I want to get a 1 plus epsilon K, which gets me 1 minus epsilon.
You're asking about approximating K.
Yeah.
Right?
Approximating K and approximating K.
Together?
Yes.
Together, actually, I don't know. Because this thing in general for max coverage log n approximation is known.
Sure.
Right? And that is again tied. But K and T together, actually, I was also wondering while preparing the talk if K and T do something. And one more result that we did not discuss here is that in FPT time, we can also have additive approximation for K. Like K plus 1 approximate solution. But in FPT time. K epsilon.
See.
Other questions?
Are there any other interesting parameters apart from K and T that have been studied for this problem?
So we can imagine that these also actually in some sense a parameter here, right? So in voting theory, yes, people study like number of voters, right? Because number of candidates is an obvious parameter. Like it's an obvious algorithm, I should say. It's an obvious parameter, obvious algorithm as well, as you can try all possible subsets. Right? But number of voters is also one of the parameter that people consider. So that also we had like I don't know which year, but few years ago, 2 to the power n algorithm for the CC like max coverage.
What is the number of voters in the max coverage problem? What will
No, universals. And that was again using we can get some FPT using DP, but 2 to the power n, which is tight, like 2 to the power little of n we cannot have. So 2 to the power n we have using the polynomial multiplication technique. Yeah, that was also a few years ago, I forgot the year.
Other questions?
But for other rules also it has been studied recently.
Yeah. Thanks for the mission. Only about is Friday should be in 211. We want to discuss this stuff.